G'day, in this video, our focus is going to be on the motor effect and how to demonstrate it. Our key aims for today are to set ourselves up to begin to look at dot point 6.2.2. We're still looking at forces produced on current carrying conductors in magnetic fields. That is the motor effect. The content statement that we're focusing on is to conduct a quantitative investigation to demonstrate the interaction between two parallel current carrying wires. This is a slightly more complex demonstration of the motor effect. I'm going to go over today a few concepts that we're familiar with already, which are going to be really important for us to begin to explain the phenomena that we observe in class when we start looking at different examples of the motor effect. So the first thing that we're going to do is focus on just generally forces experienced by current carrying wires in magnetic fields. Again, our key formula which describes this is that force is equal to the length of the wire times the perpendicular current multiplied by B. If we don't have the current perfectly perpendicular to the magnetic field B, then we can rewrite that as LIB sine theta. The sine theta will allow us to calculate for the perpendicular component of the current, and we can just substitute in the total current of the wire as it stands. What's really important to remember as well is our right-hand rule. With this right-hand rule, we have three different vectors which all are displayed to be perpendicular to each other. Our thumb always refers to the force experienced by the charged particle or the current carrying wire. Our middle finger is always referring to the magnetic field that wire or charged particle is experiencing, and the index finger is always referring to the motion of charge, so either the velocity of a charged particle or the current of a current carrying wire. When we start to look not just at the magnitude of force that's being experienced by an object which is undergoing the motor effect, the right hand rule is also going to be really important to help us begin to predict and explain the direction of force that that object is experiencing. Something else that's going to be really important today is some content that we covered in Module 4. We started to talk about the idea that wires generate magnetic fields when a current is flowing through it. And this was shown by the right hand grip rule, usually shown like this. So if we have our wire, we have our current represented by our thumb, the right hand grip rule will show us the direction that the magnetic field is being generated. Note that this is still perpendicular to the direction of current flow, but it does exist in a plane that the magnetic field essentially moves around the wire. And that's really easy to see in this diagram here on the left. So in this diagram here, we have current which is flowing out of the page, again, according to this key, which we're becoming more familiar with as these lessons go by. But again, current out of the page. Using our right hand grip rule, we can see that by the curling of our fingers, the direction of our fingers matches the direction of the field lines in the diagram, which are moving anti-clockwise. This would mean if you had that wire coming towards us, there would be a magnetic field going around it in an anti-clockwise direction. Now, interestingly, when we put two wires together, and again, this is the key focus of our practical in our next lesson, if you have two wires next to each other and they are both generating a magnetic field due to their current, the magnetic field generated by one wire is going to influence the other wire and impose a force on it because there is current going through the second wire. It is in the presence of a magnetic field, and the combination of those two will result in a perpendicular force. Interestingly, what this means is that the wires will either attract to each other or repel each other. And this is going to be dependent on whether or not the currents of the two wires are moving in the same direction or in opposite directions. I actually want you to start thinking about that problem now. If you had two wires parallel to each other and the currents were moving in the same direction for each, would the wires attract to each other or repel each other? Have a think about that based on the information that's in this video and in these slides. You may be able to have a go at figuring out before we even do it. But that will be the major topic of discussion for the period ahead. Thank you very much. In the next video, once we have seen the motor effect for ourselves, we're going to start looking at the more quantitative aspects and some equations that describe what we see. we're going to be applying Newton's third law to these concepts of current carrying wires and the motor effect. But until then, have a good one.